Welcome, everyone, to the Intel Network Builders webinar program. Thank you for taking the time to join us today for our presentation titled Enabling a Software Lifecycle for IoT Devices from CPE to Enterprise. Before we get started, I wanted to point out some of the features of the BrightTalk tool that may improve your experience. There's a questions tab below your viewer. I encourage our live audience to please ask questions at any time. Our presenter will hold answering them until the end of the presentation. Below your viewing screen, you will also find an Attachments tab with additional documentation and reference materials, including a number of websites and documents mentioned in this presentation. Finally, at the end of the presentation, please take the time to provide feedback using the rating tab. We value your thoughts and will use the information to improve our future webinars. Intel Network Builders webinar series takes place live every week, so check the channel to see what is upcoming and access our growing library of recorded content. In addition to the resources you see here, we also offer a comprehensive NFV and SDN training program through Intel Network Builders University. You can find this program at networkbuilders.intel.com/university. Today, we are pleased to welcome Manik Taneja, Product Manager, Ubuntu Core. Manik is a Product Manager in the Product Strategy team at Conical. He leads the strategic direction, product roadmap, and lifecycle of Ubuntu Core. He has 9+ years of experience with cloud and data center infrastructure and leads the work in the embedded IoT space with Conical. He has previously held roles across software engineering, technical marketing, and product management, and resides in the San Francisco Bay Area with his loving wife. Welcome, Manik, and thank you for taking the time to join us today.
Thank you, Renee. Good morning, everybody. Good afternoon or good evening, wherever you are. Thank you for joining us today and giving me an opportunity to present something entirely new that Canonical is bringing to light for the very first time, in fact. So thanks again. And I wanted to talk about what we are doing in the embedded space, in the IoT space, and how does this work relate to Intel. So in your picture today, you have a slew of devices, which are all x86 devices, from top-of-rack switches to DSLAMs to wireless access points to Intel NUC-based mobile base stations, all of which can essentially become smart simply by the virtue of the ability to install over-the-air updates, over-the-air software, and enable new functionality on the devices that have historically not been possible. So how do we enable this ecosystem of devices to function, to exist, and how do we manage their life cycle in a way that is consumable and manageable? So that's the charter of my presentation today. And before we begin, I want to do a quick introduction to our company. So what is Canonical? Canonical is the founding entity behind Ubuntu. We own the brand. We make the Ubuntu product, and we have been doing that for 12 years. We were founded in 2004, have over 700+ employees in 30+ countries around the world, with offices in few major locations such as London, Boston, Austin, Beijing, Shanghai, Tokyo, and Taipei. We have a really strong presence in the industry, whether it be from the phone to tablets to all the self-driving car technologies with the Tesla, with the Google self-driving car, with the Drive.ai, George Watt's car, and in fact, even Uber and Lyft continue to use Ubuntu every day in their products. Aside from those, we have market leadership in the cloud. 70% of the public clouds, whether it be AWS or Google Compute, are running Ubuntu as the guest OS. In Azure, we are 80% of the Linux instances. In private cloud with an OpenStack, we are 60% of all private cloud deployments. And even on bare metal, we have a significant lead in the market share. Across the board, from vendors using Ubuntu for their day-to-day operations include Snapchat, Pinterest, Reddit, Instagram, Netflix, so some of the biggest names in the industry with the biggest workloads are wanting to consume Ubuntu as the most stable platform for their workloads. So as you can see, we are able to play from the edge to the cloud by virtue of the various products that we introduced in the industry, from classic Ubuntu desktop to Ubuntu server to Ubuntu cloud to Ubuntu OpenStack, and more recently Ubuntu distribution of Kubernetes, and finally the Ubuntu Core distribution, which I manage and lead the development of for embedded devices. And why are we able to do this? Is because of the predictable velocity with which we are able to deliver releases in the market. So we have a release lifecycle where we have a new release every 6 months, and every 2 years we have a long-term supported release which is managed for 5 years. So our release naming is very simple. If we look at the top, we see 1404. That's essentially the year and the month. So that's April 2014. The next release is October 2014, then April 2015, and so on and so forth. So in this model, 1404 was our existing LTS, which has now been recently superseded in April of 2016 with the latest LTS, which is now going to be maintained until 2021. So as you can tell, we have a really predictable velocity in terms of our releases. And for these releases, we support the kernel and the root file system and the applications on top for the lifetime of that release. All the interim releases are in fact only supported for 9 months, whereas the long-term support release get much more love, much more care, and much more support from Ubuntu. And we maintain these for a 5-year period. So whenever we release a version, we pick a kernel and we try to stabilize that kernel for the lifetime of that system. And if we look at what we are doing in terms of maintaining kernels, so this is live data of the kernels that we have been maintaining. And from our 10.04 release, which came out in April 2010, and actually had a life cycle of 5 years, and the 12.04 release, which is now at 4.5 years, to the 14.04 release, which is at 2.5 years in its life cycle, to the 16.04, which is only half a year old, we clearly see a range of CVEs or issues that have been publicly notified by the Mitra Corporation as codified under the common vulnerabilities and exposure. We have fixed a lot of issues in those kernels, and we typically see these issues to spring up in any upstream LTS kernel. So when you work with us, when you consume Ubuntu, you can be assured that your devices are getting the right fixes. You're able to secure your devices. You're able to maintain your devices through their life cycle. So just on an average, we see about 80 to 100 kernel CVs every year for any kernel that we maintain. And we support those devices, and we issue proactively fixes to address vulnerabilities, to address security concerns, and provide updates to our Ubuntu community. And this is done not just for the kernel, but also for the root file system, and also for any application packages or middleware on top of the system. So this is just a good estimation of how many issues we see on a regular basis that need to be addressed. So if we continue to move forward, if we think about the life cycle of software today on devices, the way we have been making devices it's sort of been a very mutually exclusive procedure. So here I have a timeline, and let's just walk through the sample life cycle of what a device looks like today. So when we start to create any device, we pick a SoC, we start iterating on the kernel and keep developing a kernel for that SoC until all the components on that SoC have been cleanly exposed and are ready to be consumed. So let us say we started development on January 1st on an SoC kernel, and in June, we were like, we have enabled everything, and now we are ready to productize the SoC. So here comes the ODM or the OEM who are now going to design a carrier board around the SoC. And for the appropriate peripherals on the board and what else they wish to consume from the SoC, they are going to develop the board-specific package, which is going to enable the appropriate components on the carrier board, which along with the SoC comprise the actual product. So now that at this point, we started iteration on June, and in September, for illustration purposes, we assume that the BSP development is done. So now we have a fully functioning device with all hardware actually working and consumable. Next comes the independent software vendor. And now the independent software vendor is going to create a useful application that a consumer actually wants to pay for, right? So the ISV takes this board, the carrier board designed by the ODM or the OEM, working with their SoC partner, create a application that is actually monetizable. So let us say the development started in September, and by December, ISV is done, and almost in a year's time, we have a fully functioning product that's a deliverable product, which now ships to customers. So let's assume that your ISV had 3 customers, and each customer is buying different volume of the same product based on their size, based on their needs. So let us say customer A buys 1,000 units, customer B 2,000 units, and customer C buys 10,000 units. So here, because of the volume that customer C is buying, they are in a position to dictate terms to the ISV. So what will happen? Customer C says, we know that in the whole year, it took you to develop the SoC kernel to the BSP, to the actual application. There are, as we just saw in the previous slide, about 80 to 100 common vulnerabilities and exposures that have been publicly disclosed against that kernel. And who is going to fix that issue for me? And because of the volume C is able to command, the ISV will be more than happy to appease the customer and be willing to go back to the BSP and request the SoC to fix all these issues in the kernel, in the root file system, and make those available and consumable for their customer. And everybody in the value chain will see such a large volume of order, and obviously to encourage their market to grow, they would be more than conducive to work with the ISV in enabling customer C to get all the right patches, to get the right security fixes, and be able to move forward. However, customer A and B are not really in a position to have that same level of support from the ISV because of the low volume that they are purchasing. So in the end, what will happen is some customers are able to dictate terms to the vendors and are able to get fixes proactively for their software, versus other customers are entirely on their own, either having to invest in engineering resources to fix those or not fix them at all. And really, if we think about the case in a global scale where you have a slew of ISVs, you have a slew of ODMs who are all making the BSP, and software for the device, this problem only gets compounded. So every iteration further bifurcates the market, and the actual software diverges faster and faster from the truth. So if we think about the Android market today, for example, 90% of the Android phones are running a completely different Android than the 90% of the other Android phones in the market. And this is actually the reason why customers are not able to get a software lifecycle for their devices, because nobody has the resources other than the big players like Google, like Samsung, to actually invest in their ecosystem and continue to verify and provide security fixes to the entire stack. And this is exactly the challenge that we see that IoT or embedded devices face today, and which we wish to address with our new product, which is extremely relevant to how we want to move forward as an industry. So really, IoT demands security and reliable updates, right? So if you think about the IoT infrastructure in any organization, the ability to have certification, support, assurance, security, maintenance, and compatibility around their infrastructure are some base characteristics that Canonical or Ubuntu can provide, or any vendor can provide. But where we really see value is in the apps and the services on top. So imagine you have drone hardware. That drone hardware could just come with a free autopilot app, but then with additional paid capabilities, you can enhance the functionality of the drone to, for example, capture the woman in white. So imagine at a wedding, the photographer doesn't want to be bothered with actually tracking the location of the drone at all times. So he can pay for a pro app, which can now track the woman in white and take pictures of her on her wedding day automatically, right? So capabilities in software that can enhance functionality of what the device is doing with the same hardware. Or if we take it even a step further, where we had a business app where the same hardware is actually analyzing farms, analyzing avalanches, or in mining to verify nobody's left behind before an explosion actually happens. All these could simply be enabled by the virtue of deploying new software on existing hardware. So how do we do this is really with a store as a service infrastructure, which Ubuntu hosts, and are able to provide updates to software over the air to the devices on the edge and be able to deploy software for these devices. So how do we do this is entirely based on this new lightweight OS, which is really a minimal Ubuntu called Ubuntu Core. It is exactly the same set of packages that you find in traditional Ubuntu, just repackaged and consumed in a slightly different manner than traditional Ubuntu is today. So let's look at what are the differences that make up Ubuntu Core and why we thought Ubuntu Core is actually a very relevant solution for device manufacturers. So if you look at classic Linux, any Linux, whether it's Red Hat or Fedora or SUSE or Gentoo or Arch Linux, they're great, right? They have a huge number of packages in their archive, just like Ubuntu, just like Debian, and you can install whatever you want from their archives, right? So as you find packages and install packages. Those packages can write wherever they want in the file system, but they also enable new functionality to their users. But what it means is that over time, as more and more packages are installed in the system, they overwrite the file system wherever they need to do. They may write in the same configuration files in etc. They write in the same dot files in your home directory. They may bring in conflicting dependencies because of dynamic libraries that can potentially conflict with other packages in the system. And the longer a system exists in the field, the faster it diverges from the actual distribution that was actually shipped with the device. Right, so as you can see, it becomes really hard to manage the life cycle of existing Linux software because of the nature of the software and how every package has read and write access to the entire file system. So Ubuntu Core is set out to solve this problem in a really meaningful way, to really create a life cycle for embedded devices to deliver updates to those devices in a bulletproof fashion and guarantee that those updates are consumable. So if you look at the architecture of Ubuntu Core, on the right side, what we have done is we have completely decoupled the system from every other part of the system and made it completely mutually exclusive from every other part in the system. All the packages in Ubuntu Core are comprised of snaps, which we are going to look at in just a second. So at the bottom, you see a kernel snap. At the top, you have the OS snap, which is essentially the user space or the root file system. And then both these snaps exist on disk as compressed squashfs blobs that are read in memory and executed. So they're completely read-only, and they have their own dedicated writable spaces. And similarly, just like the kernel, just like the OS, every application is completely read-only and has its own dedicated writable spaces. So compared to traditional Linux, where anybody has read-write access wherever they want, in Ubuntu Core, every package is completely boxed and isolated from the rest of the system, and each snap has access to only areas where they need access to. And that's sort of the fundamental principle and architecture and design of Ubuntu Core. So it really allows us a lot of benefits. So let's look at what those benefits are compared to traditional Ubuntu. So snaps are a universal Linux packaging format. They're completely contained. They're, like I said, squashfs blobs on disk that are read in memory, decompressed and executed. They are updatable, and they are completely secure because they are always read-only. We have snap support on a variety of Linux distributions, whether it be Ubuntu or Debian or Gentoo or the Yocto project on OpenWRT and so on and so forth. And we also have a set of useful frameworks that are already ready to be consumed by any device manufacturer wishing to consume services on their devices, whether it be OpenHAB for home automation or Qt for doing graphics or ROS for doing the developing robots, for MQTT for sending messages to the cloud and messaging with other sensors in the network, to Electron, which are platform-independent development middlewares, to Ethereum. And all these are available as snaps with support for the snap packaging format across a range of distributions. So why do we see snaps being beneficial? So the biggest thing is that Snaps are completely read-only, so nobody can touch them in the system. And also, there are multiple versions of the same snap that exist on the system at any time. So if we compare updates to traditional Linux, whether you say apt-get update and then apt-get upgrade, or you say yum update or DNF update, or you say emerge update, depending on your distribution of choice, there are various mechanisms to update your distribution. And what happens? You essentially compare the existing set of packages on disk against the version of packages in the archive, figure out where there is a mismatch, get a diff for the versions which are higher in the repository, download the diff on the system, patch all the diffs on the system, and create new versions of packages on the existing system, and say, I'm done, I'm happy, I have actually updated the system. In the Ubuntu Core case, updates are slightly different. Updates are completely transactional. So whenever there's an update, system looks at, again, the version of packages in the archive, in the store, figures out where the diff is, downloads the diff, merges the diff with the existing package and the diff, and creates a new package of the same snap on disk, and essentially updates the system to now execute this new snap. So in traditional Linux, the bootloader is fairly static. You have a static path to the kernel, a static path to the init.ramfs, a static path to the root file system, and whenever the bootloader boots, it just goes and boots that same kernel, the same root file system, unless it has been instructed to do so. In the Ubuntu Core world, bootloader is fairly dynamic. It decides at runtime which kernel it needs to boot into, which user space or root file system or OS snap it needs to boot into, and at runtime, it decides and picks a kernel version, an OS snap, and executes that system. Whenever there's an update, if there's a kernel update, the bootloader is updated to point to a new kernel. Similarly, if there's a user space update, the OS snap is pointed to a new version, and the system updates to boot in that kernel or the OS and runs a series of sanity checks. So if the kernel update is a failure and there is a kernel panic, the system will automatically roll back to the previous working kernel. Similarly, when a OS snap is updated, init.ramfs will run a series of tests against the OS snap. And if init.ramfs determines that the OS snap update is not a success, it will reload the system to the previous OS snap. And each application on top, similarly, can define a series of health checks for its own application, which could be as simple as, can I ping google.com? Or a lot more complex, where the system will execute a series of shell scripts or bash scripts against that system, against that application, and ensure that we have a working application. So we can verify whether an application snap update is actually a success. And if not, we automatically roll back the application, guaranteeing that updates are completely transactional, are completely isolated from other parts of the system, and we can, in a bulletproof fashion, deliver updates and guarantee that either the updates will work or the system will go back to the previous working state and not break itself. Because either way, whether an end consumer has to bring the device into the manufacturer or a manufacturer has to roll the truck, it is really, really expensive for both parties. So with this update mechanism, we are able to guarantee the device lifecycle. We are able to guarantee that the device can continue to function without any conflicts arriving in the system because of dynamic libraries, because of applications writing on top of each other and trampling each other's resources. And that's really a unique value proposition that we are able to offer for the first time as a OS vendor. So moving on, each snap is completely confined, though it extends the base capabilities of the system. So each snap does not have its own user space. All it has is its own dependencies, its own libraries, and its own runtime, whether that be JRE or Python or Perl or Ruby, or whatever you need can be packaged as part of the application, and then that application has its own writable area. So you can be rest assured that no other application or the system can corrupt the data in your application. And all this development can happen via standard development tools and platforms. We develop on classic Ubuntu that we all know, love, and have been familiar with over the last decade. We have a simple build mechanism to create snaps, which is called Snapcraft. And this illustration on the left essentially walks you through the various stages of what the Snapcraft tool does. Essentially, Snapcraft is a single file, a YAML file, where you express what needs to be built and what are the dependencies for building that software. So you can essentially say, I have code on GitHub, or I have code in my local directory, or I have code in my version control system. This is where the code exists. This is what you need to compile that code, whether you need Python 2, Python 3, you need JDK 1.5 or JDK 2.0. The system is smart enough to figure out all these dependencies, and include all these dependencies in the program and be able to compile your software. So first it's going to pull the software, then it's going to build that software with whatever dependency that was expressed in the YAML file. After that, it's going to stage the software where essentially if multiple parts are delivering the same executables, stage will essentially choose which of those executables will actually make it into the snap. And once everything is ready to go, we will use SquashFS to compress it and make a read-only blob, which is now called as a snap, which can then be published to the store and over the air deployed to devices. So on the right, you are looking at a Dell Industrial IoT Gateway, which is running Ubuntu Core, which is a standard x86 platform where you can deploy over-the-air updates to the kernel, to the user space, to any application, and even introduce new applications on top as needed, when needed, completely remotely, without actually touching the device, and manage it in a way that we can only financially make it feasible. So with this mechanism, we are really trying to reduce the operating costs for field devices. And how do we do that? Is by virtue of a new capability that allows us to manage these devices remotely, to update their software, to install new software. So we built a new paradigm around Ubuntu Core for device management called SnapWeb. And essentially, SnapWeb is a service that's running as a web service that is exposed on port 4200 on the device. So you just go to the IP address port 4200 in your browser, and you can see and you can log into the device, and you can see what the device is, what the serial number for the device is, what is actually installed on that device. In this instance, we have a sample picture of a router which has Docker installed along with the kernel snap, the OS snap, the device manager snap, which is SnapWeb, and the gadget snap, which defines the characteristics of the device. And also at the same time, it allows us access to a Ubuntu store where now a slew of software that is relevant for the x86 architecture can be exposed and be remotely made available for the device to consume and allow the device to do something new that the device did not do before. So there's a relevant question from the audience at this point, which I thought I'll take up. So where is Docker located in the big picture? So Docker is part of the application snap. The kernel is just a traditional kernel, except is packaged as a snap. Similarly, the rootfs is a really compressed blob. It's about 45 megs of essential core packages that are needed to enable the system, and anything on top is added as a separate application snap. So here in this diagram, we are looking at Docker snap, which is completely separate from the kernel snap or the OS snap, which essentially define how the system needs to boot up and enable the essential hardware on the device. So moving on. Now that we have considered the various ways applications can be consumed on a device, what can we really enable? So if you think about a CPE or a consumer premise equipment or an enterprise gateway or a DSLAM or a base station, a mobile base station, we can truly think about some novel ways of enabling a lifecycle on the device. So if you had a top of rack switch, for example, you can just enable it with a kernel snap and a OS snap, to which you can add the control plane specific knowledge, which in this case could be FBOSS, which is Facebook's open source network operating system control plane, to more software. For example, in a mobile base station, at the moment, we can deploy a NUC with a programmable RF radio where we can, through in software, install a LTE stack. And let us say 2 years from now, industry determines a new standard for LTE called LTE2. Then we can simply install a new LTE2 software on that existing hardware and enable new capabilities on that system. At the same time, if we just wanted to do L3 on any device, we can install Quagga. Or similarly, based on our device, we can create our own private cloud by installing Nextcloud, do load balancing with HA proxy, or set up our own server with Nginx. And these can all coexist meaningfully on the same device, right? So you can have a separate intrusion detection system or a firewall if it is a consumer premise equipment to ensure that vulnerabilities from the core of the network do not make it to edge devices, or you can create your own wireless network by creating your open WRT snap and be able to install these software on the same device at the same time. It gives you really the flexibility to re-envision the life cycle of a device, to re-envision the potential of a device, to re-envision what a device is and what the device can really do in a meaningful way, allowing third-party software developers to compete for the same physical resources on your device and offer meaningful services exactly as you do on the mobile space with the iOS store or the Android store. Be able to do that on your embedded device, on your IoT device, and really rethink what the device can do and offer going forward. And that's really the core of what Snappy or Ubuntu Core enables for the device. All these software can be separately managed and separately updated, remotely updated, and consumed on any device. So the potential is really up to end developers about what they wish to consume and enable for their devices. So completely decoupled, completely independent sources of innovation, which can meaningfully coexist on any device and any hardware. So just as a reference, for a network operating system, for a data center top-of-rack switch, a standard x86 top-of-rack switch, here we have an example of a Facebook wedge, which is a 40 gig top-of-rack switch, allowing the capability to the end user to choose what control plane or what intelligence they wish to enable on that device. It could be PCOS, which is Broadcom's ICOS, or could be Facebook FBOSS, or Facebook open source software, or SnapRoute from FlexSwitch, and Quagga. And all these decoupled sources of intelligence can be installed on any device and readily be consumed for that device without having to worry about how will they interact with the rest of the system, because they are completely confined, they're completely isolated from each other and the rest of the system, so that they can be remotely managed, remotely updated, and really enable a life cycle for that device so that the device does not break itself. Moving forward, I have another example of why enabling such unique software on these existing devices that we have been developing for a really long time can be useful, can be meaningful, and offer something that is completely new and completely different than what has ever been offered before. So if you think about a data center where we want to rack and stack and stage hardware, right? So you buy racks and racks of x86 servers, you have a top-of-rack switch, and what do? All the servers are bare metal, so essentially we set up a TFTP server which has the image and PXE boot these servers. So we have a similar software called Metal as a Service, which has a region controller and a rack controller architecture. So rack controller resides on inside the rack in any server. So we can do hardware inventory, we can do OS provisioning or PXE booting, IPMI over IPMI, and also offers DHCP and DNS services through the Metal as a Service software. So imagine instead if we could just move the rack controller software, which is booting the devices in the rack, to the top of rack, giving you additional space that you can use, additional compute resources for your own workloads. We could run the mass rack controller on the top of rack switch along with its control plane and extend the functionality of the device. And then every time a device boots, mass rack controller caches the image on the top of rack, and every subsequent boot can be locally done from the top of rack switch instead of going to the TFTP server in the network and completely reducing the network bandwidth that is going to be consumed when multiple racks of devices actually boot in the network and wish to consume something in the network, right? So each top of rack switch with its own mask can independently boot up all the devices in its own rack, significantly reducing the staging time, significantly reducing the bring up time, and enabling you to iterate faster while staging or during disaster recovery, right? Similarly, you can think about the potential of installing data analytics tool on the top of rack switch to allow you to monitor traffic, to allow you to redirect traffic in the case of congestion, to install network tools for load balancing, for firewalling directly on the top of rack switch, and offering something unique for the very first time in the network. And this is exactly what is enabled by mass running as a snap in conjunction with the control plane software, which are really two decoupled pieces of software developed by completely different entities, offering something really of value on the device that can then be updated, that can then be managed and consumed in the way software should be. Right, so all this is fully enabled by Ubuntu Core. So what next in terms of consuming Ubuntu Core? Ubuntu Core is completely open source and contributions are fully welcome. They are available on GitHub. All development of Ubuntu happens on GitHub at the link at the top on github.com/snapcore/snapd. Anybody who wishes to contribute can come join us, can come contribute and enable this ecosystem to thrive and move forward as we expect with our large Ubuntu community. We have a website which teaches you how to develop snaps at snapcraft.io. You can follow tutorials, follow sample snaps, learn how to create your own YAML file, build snaps, and upload them to the public store for general consumption. At the same time, for device manufacturers, we enable the capability to set up a white label store where they can create their own brand identity, selectively choose what software plays in their store, so all their devices will only see their own store and the software that is exposed via that store rather than software in the public store, and be able to manage their devices as they should. We have example snaps available at GitHub. They're available on Snappy Playpen repo, which is available on GitHub, ready to be consumed. We have a list of tens of hundreds of snaps that are consumable today and how we actually created those snaps. So there's an easier learning curve, an easier way to follow samples, easier way to develop, easier way to look at similar instances and how people solve those moving forward. Similarly, we have really useful snaps that are readily consumable by anybody in the Ubuntu ecosystem, or with snapd now running on all the other distributions, these can be consumed there as well. So you have a Docker snap for process containers. If you want to do machine containers with the upstream Linux container project, we have the LXD snap, and we have the Quagga snap. So big differentiator, because snaps are packaged directly by upstream, they can always track upstream closely, right? So if we think about, again, going back to the life cycle of software on a long-term supported release, we pick a package version and we don't keep moving forward with the various package versions during the lifetime of that software for 5 years. So instead, the software gets stale, but is stable, so it's readily consumable, and the upstreams would rather prefer that their end users are actually able to consume software faster, consume the latest features of their software so they can deprecate older features and they don't have to support that long term. Snaps gives them that ability, right? Snaps allow developers to closely track upstream development, push snaps at the same rate at which they are developing their own software, at the rate at which they're iterating, so that the latest, greatest software, the latest, greatest stable pieces are immediately consumed on the devices as soon as they are available, right? So big advantage with consuming snaps on any device. General purpose snaps will really help us re-envision the potential of any embedded device, right? Whether it is the traditional embedded devices with consumer premise equipment, to a edge gateway, to an enterprise gateway, to an industrial gateway, to a mobile base station, to a DSLAM, to a GPON, we can really think about new services that can be offered at the edge in the proximity of the users, significantly reducing the latency in the network, significantly reducing the load in the network, and really improving the satisfaction time when information is available closer to the users in the vicinity where they are and available to be consumed in a meaningful fashion that has been very hard to do historically. So we have a lot of additional resources. In addition to GitHub and Snapcraft.io, we have Snapcraft mailer where you can post questions and we will help you move forward with your development, help you develop snaps, help you really move forward with consuming software on your device. And of course, we are also available live on IRC, on Freenode. You can come join us on #Snappy, talk to our team, and have your questions answered right away, allowing you to move forward and iterate very quickly and continue with your development as needed. And really with that, I would like to thank you for listening in to this presentation, for giving me an opportunity to introduce you to something new that Ubuntu is introducing for the very first time. In fact, the GA or the general availability for Ubuntu Core is slated for this Thursday, and stable public images for the x86 architecture, whether x86 64 or x86 32, will be made available and readily consumable for anybody wishing to use them, wishing to consume them for their devices. We highly encourage you to play with these on your device, on your NUCs, on your x86 servers, in the cloud, learn in your KVM, in Vagrant, wherever you like, and experience what Ubuntu Core can truly enable for your devices. So with that, I would like to pause and wait for any questions. I'd like to use the remaining few minutes and give an opportunity to the audience. If they have any questions, I'm happy to answer them and walk them through our thought process, our features that we really think are extremely useful for this new class of intelligent devices.
Thank you, Manik. We do have a couple of questions from the audiences that I would like to moderate for you. Why are updates relevant?
Absolutely, great question, Renee. So updates are super relevant because if you look at like all the recent cases of the malware that is getting spread, all the dynamic DOS attacks, denial of service attacks that are happening in the industry, it's happening because software that was shipped from the factory was never updated, right? As we looked earlier in the presentation, we see and fix hundreds of CVEs every year across the board in the kernel, in the root file system, in the user space, in the applications, to ensure that a system is secure, to ensure that nobody can hack into the device and use that device for their own nefarious purposes. So really, updates are super relevant to ensure that software is never stale, to ensure that software can be consumed and managed on that device for the life cycle of that device. So I see another question from the audience: can Ubuntu deliver over-the-air updates? Absolutely. Ubuntu hosts a public store infrastructure along with a white label store as a service where software can be updated, software can be uploaded, and then all the devices that are installing that software will automatically check for a update on that software and be able to consume that update completely remotely without an administrator actually doing anything and installing that latest software on that device. And all this can happen completely independent of the rest of the system. So over-the-air updates for the kernel, for the root file system, or the user space, and any application on top. So how can Ubuntu Core help monetize software? Absolutely, via the store infrastructure, ISVs or independent software vendors can upload software which they wish to sell. The store will allow users to purchase that software, the latest stable version, and really iterate on that software and enable an ecosystem of ISV developers to sell software for these embedded devices, right? Whether you wish to write a new LTE stack or you wish to write a firewall, all these can be enabled and consumed on the device via the store infrastructure, allowing you to generate revenue after the hardware sale, right? Another question I see, I've already seen RC2 release for Raspberry Pi. What is the release plan for ARM-based systems? ARM-based systems will also release in line with x86 systems on the general availability. They will be available at the same time as x86 64 and x86 32 based systems and be ready to be consumed on your Raspberry Pi 2 or 3 and be available. And I believe I see have one more question, which is designed for Docker. I believe I already touched upon it earlier, but just to rehash, Docker is a application snap that is available on the system, ready to be consumed at any time with the right features, closely tracking upstream development. So you can get the latest version of Docker over and above what is available as a deb package in the archive and be able to move as quickly as Docker upstream is moving. Any other questions?
It looks like you've answered all the questions, Manik. I would like to thank you for taking the time to provide us this informative presentation, and I would like to thank the audience for attending. This will be available on the channel if you want to go back and look through it and review any of the materials. And I appreciate everybody's time, so thank you. That's the end of our presentation.
Thank you, Renee, and thank you for everybody for your time, and thank you for the opportunity. Hopefully you like and love Ubuntu Core just as much as we do. Thank you.